operating constraints are not satisfied, and some loads are off. In restorative, of course, we are trying to restore the load which was lost, leading to emergency, and operating constraints are not satisfied. So, just for the security assessment, which sometime we call it operational reliability, because it's not a cybersecurity, it's a security is operational reliability, operational security. Uh, in different control action, which will result into. So first, when we say it's a secure, it's insecure. What do we mean is that if you do the if then analysis, that system is going through a configuration where one generator is out for maintenance or another generator is out. One line and two line, which is a double circuit line, is both out. So we make a list of those, and then we decide that if all of that list has gone through and run the power flow without violating any constraint and without violating any again load constraint and limit constraint, then we call it secure. If that is not the case, then because we are doing if the analysis, we have time, it has not happened in the field yet, we can apply some preventive control to make it again secure, right? So if it's not secure, which means it's insecure, for a specific set of contingency, we call it contingency. So line outage, generator outage is we call it contingency. So if it happens that we are not meeting the constraint, then it becomes insecure. And once it becomes insecure, we can do some preventive control before it happens to make it secure again. So now, in the real system, which means that we are operating in normal condition, we are coming with secure and insecure conditions a few minutes before it happens. So we run the security analysis every few minutes, 5 minutes, 10 minutes, 15 minutes before. And remember that we talked about two things. So there are constraint, limit constraint in steady state, and then there are limit constraint for the stability. So not every utility runs the stability, because stability is voltage stability, frequency stability, and transient stability, right? So because not everyone runs the all of these due to the computational burden that will take, plus being preventive requires you to be a little bit more, being more accurate in transient is more tricky compared to being more accurate in a steady state analysis. So the secure and insecure depends that you're trying to do the steady state security or you're trying to do the dynamic stability security. Once we do that analysis, like I said, that not every utility do the dynamic stability, but most of the utility which is large enough does the steady state security. Then the question become, in a operational stage, which means that we have done this analysis and we expect that system will not create a problem even if those contingency happen. But for some reason, like maybe contingency was more than what we have done analysis here, which means that three outages happen. You will go into the emergency scenario, and then we lose the power, and then we need to come to the restorative with certain emergency control. If you lose a power with in some way that you get to here, then you have to do the restorative control to come back to the secure or insecure, and then do the preventive control to go back to the secure, right? So it's like the whole system is on a trajectory, right? Like you're driving a car and you expect that a person, another car which is in the next lane, can come in front of you, and you will slow down or you will speed up. So that's my preventive control. And if you if an accident happens in front of you and you have to really stop, that is, kind of emergency scenario. But if some damage happened to the car, then it's a restorative scenario. And then you have to, get out, see that what's the damage, and then basically drive your car away and take it to the repair shop to again become insecure or secure. So when you take to the repair shop, it's insecure because it's already damaged condition, and then you come back to the secure. So this is exactly happen on the system also. So now, talking about more about secure versus insecure, like we talked about that we have a list, which is a contingency list of different possible line and generator outage, right? And if the system is still reliable, which means still able to supply, which is estimated to power without violating any constraint, it's a secure. And insecure, the other point is that when you do this analysis, it's being done in few minutes before. When you do it few minutes before, your system state that you have is not too much far from real state. If you do it hours ahead, you might lead to more error. If you do day ahead, it might lead to more error, right? So if you're trying to predict a way in advance, the chances of higher accuracy is less, right? If you're trying to only predict few minutes before, chances is that you'll predict it in right way, right, or very close to the real thing. So with the operating condition, the contingency which will be ranked that which is not secure versus which is secure will also change because your operating condition with the load and generation being produced is also changing. So now, each time we have a next set of contingencies which need to be added for some region or need to be taken out, we do that. And we can have either n minus 1, which means that there are n components. So there is a system in an area, again, like take a state, and that state or that control area, like let's say UP, has 1100 components, which means that 1000 lines, transmission lines, and 100 generators. So that's n, and if one of those goes out, so one line goes out or one generator goes out, we need to do the security analysis. If two combination of, so once you say n minus 2, the combination becomes a lot, right? So 1100 times 1100 will become or 1100 times 1099 will become a combination, right? That we will analyze, because we have to make a pair of two different contingency possible, right? And you cannot pair with it itself, right? So the same contingency cannot happen twice. So n minus 2 will be a lot bigger number in millions, while n minus 1 will be only based on the number of components. So now talking about how do we do security analysis. So first one is that we do the limit checking, which means that any violation on the voltage and the overload. And then we do the security analysis for detailed contingency evaluation. So if rough estimate give us that, okay, this contingency. So again, objective is that we have a list, right? So we have a 1000 possible contingency that can happen. We want to see that which one will violate, which will result into voltage at the node or overflow on the line violation. So we can do it pretty quick without solving the full power flow because we want to narrow down the list. So out of 1100 violate the limit. So now for those 100, we can run the full power flow and do the contingency evaluation. And then based on that, we decide that do we need to take preventive control because this is resulting into violation or not. And then we need to be prepared that if it happens, what emergency control we can take. Sometimes we need enough time to determine that contingency that happened, why it happened, and it's called diagnosis, and then take a restorative control to bring the system back to the normal. So normal can be like we just saw here. The normal can include both secure versus insecure because this is looking ahead. So it is looking at 5 to 10 minutes ahead. So going back to the whole process of that, how we get the data and do this analysis. Uh, from SCADA, we get the measurement, right? Then we do some filtering and pre-processing of that data. Then we talked about that we do the state estimation, which is basically fitting this measurement into the system model, because we know that every measurement are correlated with the system characteristic and system parameters. After state estimation, we can now do the security monitoring, which means that we have the list and we will run power flow like one iteration or some other way of like DC power flow. So it's a quick, and we can find out, narrow down the list. Even though now computational power has changed so much that we can actually run the all contingency and still run it in a few seconds, right? Earlier, like let's say even 20 years before, it was not possible to run millions of contingency in a few minutes. And that's why we used to select first and then do the detail analysis, detailed power flow analysis for the selected ones. And if you want to take a control action, sometime we need to solve the optimal power flow, which will tell us the control decision. But still, it's needed to select it down by rough analysis and only do detailed analysis for selected contingency. Why? Because we are not only now we are looking at not only steady state, but also dynamic stability analysis. And for that one, it does take time because you're solving a transient stability or which takes so in a power flow we typically solve algebraic equation or matrix manipulation. In a transient analysis we have to also solve differential equation, and that makes it more time taking. So before doing a state estimation, we need to know the network, which line is out, which line is in, which one is out for maintenance, or and then how do you do that? You build topology. So network topology is basically the transmission network, and we just need to update it, right? Because we already have a base case. We just need to update it based on that which line is out for maintenance and which line has a fault. So we can take it out. Otherwise, my estimation will not converge. Why it will not converge? Because we are trying to fit the measurement into the system model. If the system model is not correct because it has a line which is actually out in the field, but model has that, then my system is not correct. So we are trying to fit the system which is not correct with the measurement which also is not correct of some values. So if you try to fit these two things together, it will not fit and will not converge. So that's why we need to make sure that the state estimation has a correct system model as much as possible, and then it can filter out the bad measurement out of the all the measurement that's coming. Other thing we do that once we solve the state estimation, other than security monitoring, and then quick way to find the contingency evaluation, and then determining that what control we should be taking now or which one we can take to go back to normal state, right? So one of these and one of these. Then another thing we do is the load forecast update. So we are doing the weather based load forecast, historical load based forecast, which we take that information, and then we take the network topology, not only the one that we are operating, but how it is tied with the neighboring area, and that's the external equivalent update. And then we take it, and then we solve the load flow analysis, which will help for the contingency evaluation also, right? Because it's related. This does require your network load flow analysis. We does require load. What is the load now? And then now you're able to do the contingency evaluation and determine the preventive control. So this is called security analysis, or sometime we call it operational reliability. And this whole thing is coming from the SCADA, so data acquisition processing. Now, how does it relate to the DERs? Because and distribution system, because in the whole process that we do is really it is limited to the transmission system right now. In distribution system we do the state estimation, but we do that with aggregated system information because we don't have the complete network known and accurately updated in the control room. So we do solve the state estimation, but it is a rough analysis, and we do not do the contingency evaluation. Why? Because outage of one segment in distribution system is going to impact rest of the system less. It is not a mesh network. Mesh network in distribution system is rare. If there are any, it will be less than 0.5% in the much bigger city. Mesh network is more reliable because if you miss the one path to reach a data point which is consuming the power, you can reach from another path, right? In a radial network, that will not be possible, because if you're going to only feed, and we will talk about that more later in distributed system modeling. But now the question is that if there are DERs, it will change my contingency evaluation. It will change because it can feed the power locally. So how do we integrate DER and distribution system network into this whole contingency analysis, doing it separately but still influencing the transmission system security analysis? So this is one of the research topic. We don't have a software, we don't have a network, we don't have a solution which is already in practice in field, that how to do the security analysis or operational reliability analysis with active distribution system or DR rich distribution system. So this is some question to think about and finding a right solution for this. So let me stop here and see if you have any questions. So I see some question in the chat. Let me see if I can go to that. So first one is that operational security considers the cyber security also. So that's a good question. Right now, it does not. If a line goes out because of cyber attack, in some way it is considering that, right? But in operational security or operational reliability or security analysis, we are not looking at vulnerability caused by a cyber attack, but the impact of that, right? So it is indirectly being considered that it doesn't matter that how line and generation goes out. If it is in the list that we are already prepared with the if and then analysis, it will not cause a problem.
So then the reliability value will be it will be not correct, right? If we are not considering the all the causes.
All the causes of so reliability is only about performance, right? If you assess that something caused by cyber attack will result into the outage, then yes, we are not considering that in a computational analysis, which means that doing the simulation and figuring out for the future, right? But in the real system, when we do the reliability computation, then everything is considered because this is a real performance. One thing that I did not mention is that reliability computation, when we consider and we know that this power outage happened because of a cyber attack, we will not count that either in reliability computation. Why? Because we use that number to compare the performance of two different utility, two different operators. And if one was subject to the cyber attack and one was not, then it will be unfair to count the cyber attack. So there are these open question that what is the best way to integrate cyber security analysis into the reliability, into the operational security analysis. And these all are so new, and even though these attacks are happening, but because the outage caused by cyber attack, at least in public domain, we are not putting those information, is not very often. So what will be the best way to integrate the cybersecurity based outage practices in these operational existing practices is a still open question, and everyone is trying to figure it out. How to integrate DR, how to integrate cyber attack, how to integrate the cybersecurity analysis into reliability and operational security.
So, but in some papers, I have read that they say that using this algorithm, the attacks can be detected easily or it can be bypassed, and then hence this will improve the grid reliability. So, do they consider the cyber attack and like give these statements?
Yes, yeah, it's possible. So in research, it exists, right? You can do the analysis for a system, and you can show that reliability has increased or security has increased. Uh, what if it has been implemented in the real field or not? That is a different question, and that has not been done. So in research, there are some cases where you know, I mean, not some, but there are lot of paper where they show that with the cybersecurity being considered, and in one research paper, you can't show a complete picture, right? So it is only looking at one small aspect and one small way to find out it is impacting the reliability or not. It was supposed to, if you make the system more secure and any cyber attack that could have happened to cause the outage now will not happen, then it is supposed to improve the reliability, right? But the whole concept of integrating into the existing operational practice in the field has not been done.
Sir, and one more thing, does resiliency consider cyber attacks?
In field and in research, there are two different things. So in field, resiliency concept does not exist yet, which means that there is no software has really integrated resiliency into the operational practices. So resiliency is a concept which is slowly making its way from concept to prototype and then to the operational practice. So prototype has been done, There are some software who some company make resiliency monitoring, but it is still in trial or prototype phase. It has not been integrated into the operational practice. In research, there are a lot of paper which does show um, that how to integrate cybersecurity and cyber resiliency together and show that how the resiliency will improve. The next question is at what basis we select the contingency evaluation, what hardware software can be used for state estimation. So state estimation is building on hardware which is bringing the data, right? So state estimation is only a software because it's a set of equation we use to solve to fit the measurement into the system model. So once we get information from SCADA, which is set of hardware, communication link, and measurement, then state estimation is a software which is getting the data from the server, which is collecting all the data, synchronizing it with the time clock and all those things. And after state estimation, we get the revised measurement or updated measurement, which we call system state now. And the system state feeds into the contingency evaluation. So um, contingency evaluation requires which contingency list, right? What can go wrong, right? It also requires network. It also requires load forecasting. It also requires status of generation. It also requires what violation they are looking for, right? So all this information is fed into the contingency evaluation, and we determine that if this line goes out of the network, if this generator goes out of the network, then can we still provide the power without any violation to the voltage and without any overload? So these are the two things that we check as a criteria.
Can we develop some there are a lot many algorithms of state estimation, right? So if we use that state estimation algorithm and put it into the MATLAB and then dump it into the LabVIEW or something, and can we do the real time simulation with that? Like
Yes.
dumping into it in a LabVIEW, dumping the code or algorithm into a LabVIEW, and then connecting that with the Opalati. Can it happen?
Yes. Yeah, it's possible. So yeah, there are some paper on that also, that which takes the, when we say real time, the real time is defined in terms of able to solve state estimation with, so you tell the time that I want state estimation to solve in 30 second, in 5 second, in 1 minute, right? Typically 30 second is okay, actually, even though we can solve in 5 second, but we don't need to solve more quicker. So let's say in a few seconds, right? So you have to set the time in 5 second, 10 second, 15 second, or 30 second. And then if you can bring the data and solve state estimation within that time, we'll call it real time, right? So real time depends on two things: the time threshold that we determine, and then the setup that we put together to do the simulation, do the data acquisition, do the solution, and produce the result. All this whole process, if you can do that in the time threshold that you put, we'll call it real time, right? So this does not require in millisecond, because in millisecond, if you solve this estimation, it probably will not be right. Why? Because we need to wait for the measurement to be in a steady state. Now if you're solving the dynamic state estimation, which is a different thing, which is typically done with the PMU measurement and requires less number of iteration to solve, that will require you to solve in few milliseconds and more often, right? So state estimation is the way you would define the real time. If there is no software, if there is no analysis which needs a result of state estimation faster than 30 seconds, then 30-second becomes the real time requirement. For dynamic state estimation, I can use that for transient stability analysis, which I cannot do with a state estimation, because state estimation by definition is a steady state estimation, which means that you need to wait for transient and dynamics to die out, and then use the measurement to solve the load flow. So load flow cannot be solved, or power flow cannot be solved with changing measurement. While dynamic state estimation, we solve with the changing measurement with the dynamic analysis, but that requires integrating differential equation into state estimation. While steady state estimation is a more like algebraic equation and matrix manipulation, and so that's the difference, right? So it's a long answer, but everything comes with its own constraint and definition. So state estimations are also broadly can be categorized as a steady state estimation, which is typically integrated in the field, and dynamic state estimation, which is still in prototype, and very few utility are already using it. Okay, so looking at the next question, and with the introduction of PMU, we're still using SCADA measurement over PMU measurement, and how much more reliable is SCADA data? So this is a good question, because that's what I was trying to refer to, that with PMU measurement, you can solve the dynamic state estimation, which is much faster and more useful for stability analysis. Uh, not so much for voltage stability analysis, but more useful for transient and analysis, or dynamic analysis, stability analysis. So right now, because PMU was not put at each substation with the full observability, we cannot do the same thing that we do with this kind of measurement. Plus, it cost us more money with the, if you want to maintain the PMU at all the nodes and use the PMU measurement and integrate with SCADA. So you can actually integrate the PMU and SCADA together. The only problem will be that PMU is at faster rate, SCADA is at slower rate. So any hybrid analysis either need to be slower or need to be aggregated, or we keep it separate because it is reported at a different rate. And that's what we went. And so most of the existing field analysis keeps it separate, because if you want to integrate together and make the PMU as a part of SCADA, it requires us to increase the speed of SCADA measurement, which is again possible because it is being measured, but the communication link and all the server, which is, or all the data collection point, need to have a more powerful storage and processing time to make it happen, which again requires a lot of money. So with the PMU, we can do a lot of more thing, especially in terms of dynamic analysis, and in terms of integrating it together to do a single thing. There are roadblocks, which is mainly caused by the cost, because SCADA is slower than PMU. In terms of accuracy, SCADA is based on CT and PT, current transformer and potential transformer. PMU also using the same CT and PT, but PMU is estimating the phasor, which is going to more useful because SCADA we don't get the angle measurement. So voltage magnitude we get from SCADA, but not the voltage angle, because angle requires us to observe the signal at much faster rate and synchronize with very highly accurate clock. So in this case, PMU, it's a GPS. And because of GPS, which is very highly accurate, 1 microsecond accuracy, and even higher, we are able to observe the signal that how it is rotating on the phasor plane. And if we can observe it, we can measure the angle, which is basically rate of the change. And once we have the measure angle, we can put together a estimate for the phasor with the phasor measurement unit, which is not possible with the SCADA. It is only giving us magnitude. Angle we estimate. So in state estimation, we can estimate the angle, or we can compute the angle. We don't know that it's correct or not, but because it's fitting into the system states, most probably it is very close to the angle which is real. So in terms of accuracy, because PMU is being installed at a newer substation, because it requires faster communication signal, faster communication network. So we cannot put that on the older one because the communication bandwidth is already used there. So we are putting the PMU at the substation which is more new, which has more communication bandwidth. And because it's a new substation, so it will have a CT and PT, which is more accurate. And because we have a more accurate CT and PT, higher bandwidth of communication. So typically, it's not because of PMU versus SCADA, but because of the data input and infrastructure feeding into the PMU that makes the PMU more accurate, typically compared to SCADA. But SCADA from the same substation where the PMU is being connected will be also accurate, right? So it's not a direct comparison of accuracy, but typically PMU is at the newer substation with better CT and PT and better communication link. That's why it is more, uh, you know, there are higher chances that it will be more accurate. Okay, going to the next question. How frequently the load forecast update is being updated in distributed state estimation or security analysis? So load forecast is at the same scale that we solve power flow, right? So it's in minutes, typically 5 minutes, 10 minutes, 15 minutes, depending on different practices in utility. Then next question is that what is the standard time interval between the state estimation and utilities? Yeah, so in minutes. So again, now if you think about dynamic state estimation, which is not much in practice, but still prototype, or maybe there are very few utilities which is using it, typically reliability coordinators, that is running at much faster. So dynamic state estimation based on the PMU, one requirement for dynamic state estimation is that you have to have this fully observable system, which means that every node has to have a PMU with all the lines and with all the nodes being read by the PMU. Because if you don't have that, then you don't have the full observability and you cannot solve it. So what utility did is that they said that okay, we don't have a full observability, but we are going to reduce it to, let's say, certain voltage, right? So you said 132 kV or maybe 69 kV and above will be monitored by the dynamic state estimation and the PMU. So standard time interval changes based on minutes to several seconds. if it's a state estimation versus dynamic state estimation. So contingency analysis, which software are best to do? Uh, I think the contingency analysis is pretty standard, which means that the requirement for the mathematical computation is not very complex. So any software will work, either it's a Siemens or it's ABB or it's GE or any other software. There are like tons of software that is being developed by vendors. Same thing for OPF. OPF is a little bit more complex because it is a more nonlinear optimization, depending on different thing that is being considered. So, but OPF also comes with same vendor, and which one is better depending on it's there's no direct comparison because this is being customized by utility requirement. If we are looking for research, then for OPF, like Mat Power is pretty good, which is free, and typically get much more advanced solution embedded into that. Sometime you need to use and call some optimization external software like Groovy, and there are several others. Uh, if you're trying to solve a OPF problem with optimization requirement, which is very, very highly nonlinear, it's really good to consider contingency analysis in the distribution system. So yeah, this is a good question, which I also have a question because we don't have the answer for that. Uh, in terms of doing it and is it useful or not, I think I will say yes, because as the system is becoming more and more active and there are bigger industry load, because outage happen in distributed system, right? So load are always connected, most of the time is connected 99% of time in distribution system, not in transmission. So if you do the contingency analysis in distribution, we can increase the reliability of the at least the bigger customer, right? If not the smaller one. And because there are DRs being connected, there are microgrid being connected, it will help, right? What will be the cost of, in like a cost benefit analysis? There will be cost that comes with that, and we need to just compute that is that justified, right? So I think that analysis has not been done thoroughly, and still it's a new topic to investigate. All right, so let me go back and finish this part so we can talk about distribution automation and more focus on distribution. So different software which are there, and sequence, right? So we need to do the state estimation, we need to do the security monitoring, network topology is required to be estimated before we solve the state estimation or even solve the power flow. External system equivalent model is needed so that we can see that how much power is flowing to the neighboring state, because we don't know the model of that, but we need the equivalent aggregated model for all the neighbors which connects to the power network that we are trying to solve. Then power flow, online power flow, because it's running in the minutes, it's not a offline power flow planning. Then optimal power flow we need to determine the control actions, and then the contingency evaluation is needed, right? A lot of time when we do and see the violation or limit being violated, or limit being not met, we do the alarm processing, which means that we have to look at all the alarm which is saying us that something is wrong, this voltage is off the limit, this power flow is off the limit, this power generated is off the limit, temperature is very high in this transformer, all this different kind of alarm, the fan is not running in this substation, right? Which of course will result into two alarm, right? So fan is not running and it's being heated. So once we get all these alarm, we need to first find out how critical is this alarm? Is it normal or it is not? If it is alarm is not much there, and temperature is high but everything is being met, so we are still in normal, right? We need to do something, but we don't need to do something immediately. So if we are still operating normal, which means that there is no violation and there is no outage, we will call it normal, even though alarm is still coming and saying us that there is a more heated generator at this location or transformer or line. We will do the security analysis. We will do the transaction as the power transfer is needed, and then apply some preventive control that okay, why it is heating, and make it less, redispatch the generation, less, like make the power out of that generator less because it's being heated, or transformer. We need to find out that is it why it is being heated, and make the power transfer through the transformer less. So that's all preventive control, right? Before something wrong happens. If alarm is saying it's not a normal, which means the outage already happened, something is out, then we need to find out why the outage happened, right? And then look at the fault that caused that outage, and then take the remedial now. So we cannot take the preventive, but we have to take the remedial and fix and bring that power back to that region. So here are some of the energy control center that how it looks like. Every utility has a different. Typically, there is a big monitor on the screen on the wall, and then each operator which is looking at different aspect. So someone is looking at that, is power transfer to my neighbor is same as we expect, as we planned. Someone is looking at that every voltage is good. Someone is doing the security analysis, which means that they are looking for the future if then analysis, that if this goes wrong, what will system look like. Someone is looking at renewable generation. Someone is looking at the frequency stability analysis, right? So every desk has a different job, and that's what they focus on. All the information is shown on the top, so that if you in one of the operator desk depends on operation of someone else, they can look at the big picture also. There is supervisor also. There is a support team of engineers that they are helping them, so they can ask, they can text, and ask that, give me this and give me additional information, and that's they get, and they are the responsible to keep the power going and minimize the outage. This control center has evolved over time, and if you think about different applications that has come in the control room, this mainly happened first. It was all paper, right? There was no computation, and then we were operating more relying on the automatic control, and then being reactive as things goes wrong. But then we realized that after a big blackout that happened in 1965, that we can use computer and then can solve things more quickly. Then we added security application in 1970s, and then the state estimation and security analysis are very common now. Most of the bigger utilities do that. Very small utilities are still not doing state estimation, even though they do have capability, because the data that they're getting is not right, and it requires some more money to put there to make the data right. But most of the bigger one are using all this information. There's a good paper, in 2005 that was published on control center and how it is evolving, right? So control center also evolved as computing evolved. So we had a computer, personal computer, then there was server, then there was a network computer. Now there are GPUs which can do much more. Now there are cloud, right? So cloud integration into the control room has not happened much because of privacy issue, but cloud concept has been applied to some of the centers. uh, GPUs and what is the need for that will be the next thing with especially the machine learning algorithm and the cyber security. So all these things and information integration. How do you bring the information so that, yeah, there are two objectives, right? That we want operator to make a right decision, but the second thing is that we want them to not be overloaded with information. They cannot make a decision if there are too much information is displayed on them. Other thing that happened in the past was deregulation or the market, and that came in 1990. That resulted into a different set of software being installed in the control room to monitor the market. There was ISOs, which is Independent System Operator, which is typically a collection of multiple utility coming together and setting up this non-profit organization, which will monitor them overall in terms of market. There's also this RTOs or regional transmission operator, which is looking at the bigger region beyond the utility areas, and they help each utility to operate together. Electricity market like had changed the way we operate the control center. Like I said, that 1990 and 2000, uh, it is not everywhere. So electricity market does not exist in each and every region, but I would say almost 50%. And now DUMS, which is DR management system, is being integrated into the control room. Other than all these new concept, cloud and cybersecurity concepts, which already existed in different control center, which is, we talked about that network operation center and security operation center. But what information needs to be exchanged, that is still evolving. Does not much exist today. And then GPUs. So how does market work? Very quick overview. So you got this generation, transmission, load, right, and distribution. We run the transmission energy management system, which has SCADA, the information. We run the state estimation, we do the contingency analysis, and then we do the OPF. OPF takes the form of unit commitment. It is a security constrained unit commitment. What it does is that tells us that which unit will be on, which unit will be off, to keep the cost lowest, but also security constraint, which means that even if one unit, which is generating unit, is off, we are okay. We can still provide the power to the all connected load. So that's why it's a security constraint. And then once you know that which unit is on, we need to determine in real time, which means that every few minutes, that how much power to generate from that. And that is called economic dispatch. So that the cost is lowest, at the same time security constrained, which means that even if the generator fail, we're okay, right? To provide all the power to the connected load. We have to use AGC, so we have to send the control command from SCED and SCUC. Typically, this is done in hours, and this is done in minutes. So from SCED, we have to send the command to the generator that how much power to generate, and that is done through the AGC, right? Automatic Generation Control. So this resides in the generator unit control and also get the signal from the control center. And sometimes you have to do the load management, right? So this is the first part which already exists in the transmission system. With the market operation, we added a new part, which is the competition. Who will provide the generation? Who will generate the power? And to decide that who will generate the power, which is the most competitive, we need to plan ahead, day ahead, hour ahead, right? So that in real time we exactly know that who is providing the power, right? And that we can do in two ways. One, in real time we can determine that who will provide the power. Our generator can sign a long-term contract at certain rate, which has to be competitive enough that they will be accepted and contract will be signed. And then comes the day ahead schedules. So in day ahead, we basically try to minimize the cost, and we choose that which generation will be accepted in the market. And then once they are accepted, then we do the dispatch with the hour ahead adjustment, which is basically determining that how much power to generate. And then we dispatch the power real time. But what we told the generation to do to give us the power to meet all the load will may not be the same thing as needed for as we told them, right? Because some load has changed, some contingency has happened, and then some load has increased, some line went out. So the real time dispatch which happened may not be the same thing as we told for hour ahead or minutes ahead. And that's why billing will be slightly different than what was planned. So this is all market driven, where we do not minimize the cost, but we minimize the um, social welfare, which means that maximize minimize the cost of load and maximize the profit of generation. And that's what we take in market. And that's a big difference between the economics based operation versus market based operation. So in market based operation, you're operating the grid as a business, where supplier need to make a profit, and demand need to minimize its cost, and both together becomes the objective. Instead, in here, where we are only trying to minimize the cost. So how do they know that what cost need to be minimized? Is basically we get the offer from generation. They will say that I will provide the power at this cost. Another generation will also give another cost estimate, and then we solve this whole thing and give them the price, right? And then finally we do the settlement after this process and do the bill. So there are a lot of players in the market. ISO, independent system operator, which solve this market operation. There's RTO, regional transmission operator, which provides the transmission. We try to not. There's a different model in every country, in every states, but we try to not introduce competition in terms of who will provide the cheaper transmission, what will be the bid. But we try to do that only at the generation level. In some countries, in some places, we also try to do the market competition between the different transmission provider, which is a little bit risky, because if your generation is accepted and transmission is not, it's a problem, right? So if you do the transmission market, you have to do that much in advance, right? So again, that's the main difference, that it is not a cost based operation or minimal cost based operation, but it is a business, which means that maximize the profit for the stakeholders and minimize the cost, both together, and it does result into a different solution. Generation companies is of course important, which will bid in the market. Load serving entities, so now we got this new entity which represents a group of load, and they will say that we will consume the power at this rate, and they bid also in the market. And the control center, which play different roles in different levels, right? We have same SCADA and AGC, which will feed and take the control action. It does the load frequency control, which means that it adjusts the frequency, it drops the load as needed. If the frequency is higher, it drops some load. If the frequency is, in other way, if the frequency is high, then it means that generation is more and load is less. So it has to drop the generation. If the frequency is low, then it means the load is high and generation is less. So it will do the opposite way. Load forecasting, which will be looking at, basically at minute scale, and provide what is the load looks like. And then RTU communication, right? So these remains the same even in the market. This also remains the same, different application in the EMS topology processor to tell me the topology, state estimation, contingency analysis, voltage stability, power flow, transient stability, all those things will remain the same. And then comes the all the data that is being stored, so operational data, real-time data, and historical data. In bilateral, in market application, we solve different things. So bilateral transaction is basically the deal between two different stakeholders. We already talked about SCED, which is Security Constraint Economic Dispatch, which will give me the solution that how much power each generator should generate while still keeping the security constraint, which means that even if the one generator or two generator goes out, we are safe. We can still meet the demand. Unit commitment, which unit is on, which unit will be off for the minimal cost or for maximum social welfare. Now the cost at each node is going to change. That's the biggest difference with the market. So before, cost will give the price at each node same. But in the market, each node in transmission system or even distribution, if you have a distribution market, which right now does not exist, uh, research exists though. So the nodal cost will be different in a market, and that depends on the uh, congestion on the line. So if the line is overloaded, the cost will be different. If line is not overloaded, the cost will be same at both the end. Then the load forecast and then the outage management is same as before. And then monitoring of compliance, because there are a lot of entity which need to get the data so that there's no one is making more profit than they should make. We need a lot of software and a lot of platform for this to get the bidding and schedule management and also market information publishing. We need a commercial system for settlement of the cost, and then we need the billing and credit, and also a system for metering. So different thing is required in this, like local area network with all this computing power. We need a control center which will do the market uh, supervise in ISO, and from utility control center that need to be sent to the ISO. And then SCADA and EMS remains the same, and then market participant should also get information from that same platform. So different relation, like we got this energy management system, which is generation, transmission, and load monitoring. DMS, which is distribution monitoring, and then the contract schedule is being provided here. From here, its operating constraint is going to the business management system, which is market operation, and market participant, which is load serving entity, and generator, or the one which is giving you offer that I can supply at this power at this rate. We solve the power, we give it to management system, and then we take the operating constraint back. Of course, DER, so DER and renewables is being integrated, cybersecurity, distribution automation, which we'll talk next. And at the same time, we want a more open, more flexible system to operate the grid while integrating all these new changes and decentralization, which typically means that we don't want to give transmission, generation, and everything together to a single entity, because they will be in more advantage. So decentralization is required before we implement the market. To handle the challenges, there are some enabling technology. Of course, we have a more advanced communication protocol, distributed computing system, distributed generating system, and with all these things with the object technology and component technology. And then there is a middleware, which is a technology to connect things. And then the other thing is this computing technology, which is agent technology. And then we have a lot of these new sensor, which we already talked a little bit, PMUs, PMUs, which is in there. And then we have a data science and machine learning kind of solution, which can be applied, which will look at some of these, and several different control and optimization. Now this control center is also evolving, um, in terms of SCADA, EMS, and even battery management system. But here we have a control system, which is a market software. So all these things, how do we coordinate? Because it is different software. How do we, do the distributed SCADA so it can feed to the distributed management software? SIM, which is if you change one software to another one, then it's a common information the interoperability of different software, right? So if you work with a software and you want to make it interoperable, if it's taking the same format, it is very easy to change, right? So you can replace one software made by one company to another software made by another company very easily. If the common information model does not exist, it's very tricky, because you have to, if you replace the software, then you have to build this translation for making the data right. And then middleware based distributed EMS and platform which connects two different things together and make the, I mean, there is, it's much more complex, but we're doing the introduction, so very quick way to interface two different set of software. uh, so how the future control center will look like, of course we want a very fast data acquisition system, right? And then greatly, kind of extended application, because there are new software and something is running on that. There are several, in terms of enterprise grid, how do we coordinate between multiple different grid working together, right? Which is basically neighboring system. And that control center need to talk to each other to coordinate, right? One example is that if something goes wrong in one control area, every other control area will also see the impact, but they need to know that this challenge is happening in this control area, and how to solve it. How to share the computational resources? You have a one PMU which will be helpful for another neighboring utility, but how do we share that without doing the privacy issue? And then use of service oriented architecture, which is called SOA. Then distributed data acquisition processing services, which is another one, and then distributed control center applications. So continuing on, like other thing will be that how do we how do we monitor the market so it is not benefiting someone? How do we integrate the PMUs? Dynamic security, which is possible because of PMU at the fast rate of data. How to visualize so that operator is not stressed out with a lot of these information. How to make the system more self-healing and resilient, and then how to keep the system more secure and cyber resilient, which is of course you know topic of this whole course. Also how to manage the security so it becomes more easier for them to manage. And that lead to like multiple layer cyber physical electric power grid, that because that's what we have and we're trying to monitor and control it. We do have a very good management system and transmission. pretty good in generation. Distribution is not fully observed, but we still have a DMS, distribution management system, ADMS. We also have a DR management system, but this whole chain is not much there, right? And then we have a customers, which is putting in more renewable energy now in different zones. So the process is basically the one which is a physical assets. Then there's a field, there's a station assets, then there's operation and the enterprise level, and then market level. All these together, we can only get the data out of this because of communication layer. So that is a green one. And then from there, we get a lot of data. We need to change it to information useful to make a decision. And those information should feed to the different functions so we can make a decision. And the top of that, everything is being done because there is a business layer. Someone is making money out of this, and someone is getting services. And
So,
yes.
so actually, your voice is it's not clear. It's like breaking in between.
Okay. Is it for everyone or?
So like around
For
for
me
many.
also, it's breaking.
Yeah. Yeah. Looks like someone can hear okay and someone cannot. Yeah. I'm not sure if it's an internet problem. Maybe some internet outage in India, because here I am getting pretty good signal. Yeah, so let me continue and then I will finish this part because this is the last slide anyway. Then maybe we can take 2 minutes break and then see that what is the problem. So, so the top layer is business and political, which we need to make sure that all the rules and compliance is being followed. So rest of the course, we are going to talk about some of these layers and mainly focus on this information, which is a and communication and function, which is basically makes the cyber layer. Okay, so we'll stop here and maybe take 5 minute break. Uh, and in the meantime, I will seek some help from IIT Jammu to figure out that where is the problem.
I think, sir, there is a synchronization problem because sometimes your audio and the movement of your lips is not synchronized, as well as sometimes there is some fluctuation of the voice and
Mhm.
picture block. So no problem, sir. Let us see. Let's take a 5 minutes break. I will
Yeah,
also.
but because some of the okay, okay, because some other can hear me clearly, so looks like it's not a problem from here because I'm getting pretty good internet signal here.
Yeah, okay. No problem, sir. No problem. Let me ask Vasu to see something.
Okay, so
Yeah,
we'll be back in 10:05. Yeah, so that'll be in
sure,
three
sure,
minutes maybe.
sure, sure.
Okay. Well,
Yes,
yes, I
sir.
was asking
Yeah.
if you have more questions, we can address them now, and then we'll start with the next section, which is distribution automation. Please, the voice is okay now?
Yeah, now it is okay. I think there may be some problem from our side because someone are saying they are hearing you better, but in IT campus,
Mhm.
maybe some issues in our campus.
Okay. Yeah. So yeah, it should be because it should be through Google server, right? Not
Yeah.
through Jammu. So
Yeah.
I think it should be okay. So let me answer this question: can a bigger player on distribution grid, say generation and supplying large peak power peak load, manipulate the energy market? So very good question. Yes, if the mechanism exists for a distribution grid connected PV uh, to bid in the market, which actually exists in US, they can they can manipulate the market because by I mean, of course, depends on several different factors, right? So they have to be large. That's the first thing. Second thing will be that they have some control over uh, congestion on transmission, and then playing with existing rule that exist with for the market. Okay. Well, so now the introduction part is done, which was important because we need to look at that. How do we operate the grid? Even though it was pretty quick and not much detail, but it helps us to know that it helps us to know that how it is different than distribution system and how it should be modified to to take the DER, because those are all designed without considering higher number of DERs and active distribution system and cyber resiliency and cyber security in mind, right? Other question that I see is that use of AIML for cyber attack detection, still an active and open research area. I would say yes, even though the number of paper that has been published is lot, and we will, I think it's next week when we talk about AML for detection. You will see that it is being. I mean, we will talk in two different ways: one using the cyber data and one using the power data. And I would say that maybe detection for both together has a lot of publication that has happened, but how do we coordinate that is still not very well explored. So I think it will be better answered after we have gone through the whole process, because we have 2 days of AIML for cybersecurity detection next week. Okay, so let me share the next part, which is distribution automation, so we can quickly go over that. And starting tomorrow, we'll be doing some hands-on, OpenDSS modeling. So next thing we are going to talk about is distribution automation, which is, is a natural kind of changeover from transmission with and then EMS, and then talking about that how it is different with distribution and DR coming, right? So distribution automation is something that has been going on from, I would say, almost like 20 years, and it is slightly adapting with the DR integration, right? So this part relate to the, we talked about operation with DR. Now we are talking about distribution automation, and then all the other topic are left, right? In next, this is second day, so next 8 days. Distribution system, as we have discussed about in the past, that you got transmission here on the left side. We got a market or no market, it might exist. We got a customer here, right? And then we got a operation, which is basically not only a distribution management system, but also crew management system, also the outage management system. All those things is represented there. We have this, the blue thing, which is basically the electric wire, and the yellow thing actually electric wire, and the blue thing is communication link, right? So yellow dotted line is a electrical line, which is where the electrons are flowing.
Excuse me,
Excuse me,
sir.
sir.
Okay.
Yeah.
PPT is not visible. The slides are not visible.
Okay. So it was visible before, right?
Um, no, sir. Actually, we can't see we can't see your presentation slide. It's presenting something, the black screen.
So no one sees the slides.
No, sir. It's we can see some black. Yeah, black screen.
No, sir, it's not visible from my side.
Yeah, I'm sharing exactly in the same way that I was sharing before. Do you see it now?
No,
No,
sir.
sir,
Actually,
it is not visible.
yes, sir. Not visible.
Okay, let me try to disconnect and join again and see if it helps.
It is
Yes,
visible
sir.
now,
Now it's
sir.
visible.
Excuse me, sir. You are not audible, sir.
Sir, we can't hear you, Anurag sir.
Yeah, how about
Now
now?
it is fine. Now it is fine.
Okay. Okay. So let me talk about this. So we are talking about the next part, which is distribution automation and DERs. And we talked about that there is a transmission system, right, which is here. Then there is this yellow dotted line, which is electrical system, distribution line, and then there is this blue, which is a communication link. We also have a distribution management system, outage management system, ADMS here, and we might have market or we might not have market, right? Then there's a customer which has DERs connected here in electric vehicle. In this whole system, we typically have, we may have a storage, we may have a distributed generation, which is, like solar or like a backup generation, gas generation or diesel. And then we have this transformer, which connects, once we start from transmission, and then the load with the switches. We do control, we do measurement, we do protection, we do recording and optimization also in the distribution system. So a typical distribution feeder will look like this, that you have a circuit breaker where it's connected to the transmission substation. And then we have a multiple feeder coming out, which is feeding into the different part of the city. Typically, transmission system comes all the way to near the city. And then we'll have a substation, which will feed into the multiple part of the city, right? Or the village or the town. One of the feeder, it will be all similar, but one of the feeder is basically could be 4-wire system or 3-wire system. If it's a 4-wire, it will have a 3-phase and ground, right? Or basically neutral. And these 3-phase and neutral will go into a different part of the town. And 2-phase will typically feed, while 3-phase will feed the industrial load. Sometime we have this combination of single phase, 3-phase going into different part of the town. And each phase will end with, at the transformer, where it will feed to the house, or near a transformer, which will feed it to the commercial location or industry location. Some of these are also going to end with open tie switch. And that means that it is going to tie with exactly another feeder like this, but normally open here. And if I close it, I have to open somewhere here, right? Why? So that these houses can be transferred from this feeder to another feeder, which is neighboring. Okay. And then we have this sectionalizing switch, which can open this whole part with a reclosure, which can reclose by its own once the fault is gone. So reclosure is just a switch which sense the fault, open breakers, but once the fault is gone, it does not know the fault is gone, but it will try again to close. And if it does not see a fault, it will close the circuit. If it sees a fault, it will open again. Sometimes we set it up to try 3 times, which generally means that a lot of these faults are temporary. So fault happens, but it will be lost, right? It will be gone in few minutes. And that makes sense that we close the reclosure to try out, and once it happens that fault is not there, then it will keep close. But if after 3 times, it will lock out, which means that it will not close, but manual inspection is required that why fault is still there. If it is caused by like a bird or a squirrel or something like that, it will be temporary. And that's why reclosure will close that and everything will be fine. But if it is caused by a tree falling on the line, our pole has gone bad because of a storm, then this reclosure should, after 3 trials, should keep it open. And we need to send a crew to fix that fault, fallen line because of tree falling, and then close it. So there are some 3-phase load. There are some single phase load, which is connected here. And then some of these laterals are tying with the exactly same feeder. So maybe feeder 4 is coming here and tied here, right? Feeder 2 is coming here and tied here, right? Not each, but there will be some normally open. So we have a flexibility to isolate from here and feed the whole thing on the neighboring feeder. And as many redundancy we have, the chances of outage will become less and less after fault. Why? Because if the fault happens, we will open it from here and close it from here, right? We do want to operate radially. That's why if you close it, you have to open from here. If you close it, if you open it from here, then you can feed it from here, right? And then there is also this, multiple switches on the way. So it has multiple things. We could talk about substation, which is right here. It has transformer, which is near your building and house. And then one transformer, which is tied with the transmission system. And then transformer, which is feeding to the three-phase industrial load. And then, feeders, which is basically this whole thing. It is feeding to the load. That's why it's called feeders. Then sectionalizing switches, which is here, which can make a two section. So we can take this section to another feeder and this section to another feeder. And then capacitor bank are typically connected to keep the voltage within the limit, because as it starts from here, we feed the power, but over time there will be losses here and the voltage will go down. If we feed the reactive power here or compensate it, balance it out, then the voltage will become again better here. And that's why cap bank is typically put towards the end, but not many. Then there are voltage regulators, which will be also installed here, sometime even here, which will observe the voltage and do some control action. DERs, which can be anywhere, right? And also sometime we have an overhead line and sometime we have a cable. Most of the bigger city will have a cable nearby just because of safety reason, but it costs 10 times more to have a cable compared to overhead lines. And then we have a customers, which is three-phase, which is high tension or high voltage line. And then LT, which is a low tension or low voltage customer.
Sorry, sir. Is it not visible, sir?
What's that?
Basu, sir.
Are you able to see?
Gazanta, are you trying to say something?
Everything is okay. Everything is fine.
Okay. So this is we call three-phase unbalanced because the load are more here, load are less here. We cannot control that. It depends on how someone is switching in and switching out some of the things. And also because of this high, it makes distribution system different because resistance is high and inductance is low. Why? Because this is shorter and not operating at very high voltage to create a higher reactance between earth surface and the line, right? So if you know that how capacitance work, we know that reactance and capacitance will be low here. So the next become that what are the different issues which we already have discussed. So we'll go very quickly through this. Reliability, which is the most important. We are doing everything so that system is reliable, able to feed the power to the load. There is a fault detection, isolation, service restoration in place, which is part of the outage management system or ADMS or DMS. Quality issues, which is power quality, because our appliances are designed to operate at certain voltage, at certain power factor. And if the quality is really bad, the life of that appliance, either it's a fridge or it's a TV or it's a mixer, will go bad. So we need to keep the power quality in control. Efficiency is of course important because someone is paying the bill for this, which is typically the customer. If efficiency is bad, they will be paying more bill. And if the losses is bad, then no one is going to win with that, right? So system is in loss, and so that the customer. The unplanned growth of electrical power network, that is one problem, because we typically build and extend distribution system as the need of the customer. And if it's not planned, then it's a problem. Complexity with increasing network, increasing number of electric vehicles, DERs, cyber network, IEDs, its system is becoming more and more complex, which means more number of component and dependency. Cost, we need to keep it minimum, and the time to meet the requirement, like restoring it, should be done as quickly as possible. So distribution automation technology, what does it mean? That we are basically using the digital technology, which is a communication network, sensing, to do things which we want to do with distribution system at faster rate, right? So we are putting a lot of this intelligent devices, and we want to use the data to do the automated way of detecting thing, and automated way of taking action through set of software, which is either running at the pole top, in a box, or in the ground, or in the substation. There will be engineering analysis software, a lot of data acquisition and control, which remote terminal unit, relays, digital multifunction meters, remote tap changer. We already talked about some of these, and then communication hardware and software, right? What we want to do with this, that of course we want to monitor it, we want to control it to keep the maximum reliability possible. So the power outage can be reduced by automated control. That's even better than letting DMS and ADMS try to solve that and figure out that what is wrong. Of course, try to manage it, optimize it, and protect it is other thing, which is leading to the same thing, which is reliability and efficiency. So minimal thing that distribution automation should do is measure, protect, do the protection, do the control, monitor all thing that is remotely located there. It should integrate all the component together to, for performance analysis. It should do the detection of fault and isolation of fault, which is based on protection, but minimal set of area. It should integrate all the metering and to make sure that to avoid manipulation and loss of revenue. It can also help with the automated billing and collection, right? It should do the load shedding automatically if the frequency is going down. It should also integrate the GIS map and network topology and network components together, and make its all effort to, and we're all talking about in automated way, right? To increase efficiency and reliability and make the operation easy. There is also this, we get, how do we know that there is outage? We can figure out from the data, but mainly we figure out through the trouble call management, which means that customer calls that they are out of the power. And distribution automation software, which is also, so distribution automation and DMS, what is the difference? DMS is a software running in the control center. Distribution automation is a set of all the digital control, which is automated in the field. It's just like you have a SCADA, right? So distribution automation is SCADA and distribution system plus software in control center plus automatic control in the field, right? So trouble call management is very important, because if we need to figure out that where is the outage by customer call. If the customer is calling that power is out because their fuse is out, we should be able to figure that out through multiple call and no problem in the distribution system, right? But power is still out because the fuse is blown away in that building. And able to differentiate that with a fault in the distribution system, again, to do that as soon as possible is important. So there are different application, substation automation, feeder automation, customer level automation, and then that result into a lot of different network configuration in terms of locating the fault, restoring it, service, and balancing it. Distribution automation also help with the integrated volt work control, metering, automated load sharing if the frequency is down, which is rare, but it happens. Load management and also automated mapping and facility management. Trouble call management we already talked about, and serving, doing the survey of load and energy accounting. So different function that we do, we have to acquire the data, right? So acquire the data from all the sensor, either it's circuit breaker or it's a load tap changer, cap bank, transformer. Need to control, give the control command back to the circuit breaker, tap changer, cap bank. Need to locate the fault, isolate the fault, service restoration for all the load which has been outage, and then also do the reactive power control with the volt power control. So this is substation level, right? At the feeder level, we have to look at the recloser, we have to look at the voltage regulator, if any, in the feeder. We have to look at the cap bank also, sectionalizer, line switches, fault indicators, and use that information to control recloser, regulator, cap bank, sectionalizer, and line switches, right? Also the same thing, that we have to locate the fault, isolate the fault, restore the service, and reconfigure the feeder. Now this part is happening automatically. Substation is aware of that what is happening, but as a smaller level we do, management will be even better. It will cost you more, but it will be better. And then at the customer interface level, we have to do the automated meter reading, right? Which is, someone used to come and read the meter, but we can do that with smart metering. Also do the reprogram remote time of use meter, which means that we change the price, that what time it's being used, remote service connect and disconnect, and then customer claim analysis, right? So let me quickly go through some examples, and then we'll stop today, and then we'll continue talking about DR. So give me 5 more minutes, and then we can take some questions. So in this feeder, this is the transmission. This is where it's connected, right? This is another one. This is another one. This is another one. So here is the transmission, and then we have a feed, right? Different feeder coming. There's circuit breaker connected, which is normally closed. That's why it's red, means hot, which means that the power is flowing from here. So this is feeder 1, this is feeder 2, this is feeder 3, this is feeder 4. And then we have to have this normally open, otherwise it will be loop, right? So to make it radial, we have to make it open. And then we also have this another to normally open also, which is green, means it's open, it's not hot. And this will help to configure the system in multiple different ways. If the fault happens here, like let's say here, then we can open this and connect this part into here. So we'll close this and the power will flow like this, right? Same thing here, that if the fault happens here, we can close this, and then both of these feeder will connect it to the feeder 4. So a lot of these configuration is possible only if you put this normally open and normally close switch together, right? So what does it represent? That we need to know that which is open, which is closed, and we need to make sure that there is no loop formed, otherwise protection will not work. We need to know that which is live node, which is dead node by voltage indicator. We need to use the load current. We need to know the fault current indication. And then also recloser lockout that we already talked about, that the recloser will try to close multiple times because it does not know fault is still there or not. But that's the quickest way to restore the power automatically, right? Just keep on trying 3 times, and if the fault is gone, then the power is restored, right? If the fault is still there, then lockout. Then and inform the basically operator to send the crew there. Abnormal condition we need to know, and then a lot of other component that need to be going there. So distribution automation control objective is that reconfigure after the event if the outage is there, and especially if the fault is permanent, right? So we need to restore the power and then try to fix that part where the fault happens. Some of the load will be always lost because it is really next to the fault, and we cannot restore them till the fault is removed. If conductor is open for some reason, we need to fix that, and then coordination in the protection and other things need to be fixed. Multiple fault creates more complexity. We need to determine that and then do the overload condition. Objective is same, that abnormal condition need to be detected, limit need to be detected, and like some example, like let's say this is lost, right? So this is connected to a transmission system right here. There's a transformer, right? Fault happens here. So the quickest way to restore it will be that we open it, right? But now this one is connected, but there is no power flowing in this because it's not connected to anywhere, right? R10 and R11. So what we do is that we close this one. If you close this one, then the power will flow from here to these two and from here to these two. So now every power is restored. All of these switches try to multiple load, right? So there's lateral here, lateral here, lateral here, lateral here. Here is also, here is also. So it is all feeding, the red switch is feeding the power to the load. So how do we know that what is the best way to reconfigure, right? Which one to restore? How do we make sure that we do not pick up the load which is more than its rating of the feeder and conductor size? So in this case, let's say this is the fault happens here, this is open, and this R12 by closing it becomes overloaded because these two load are more than it can handle right here. So what do we do is that we also close this one, which is loop formation, and we need to fix that, and we open this one here. So now by opening this one, there's no loop, but the power is fed from here, right? And then here also it is feeding to some. So in this way, the overload become less here, and the load is still being fed. So automation impact is that we can minimize the outage with the whole thing, and then like let's say this is the shaded area by closing the. So this is more like real feeder. This was of course representation, but it will look like this: that there is a substation. This is the feeder 1. This is the feeder 2. There is another substation that is feeding from somewhere else, like from here or from here. And as soon as the fault happens here, this will open. So this part is out of the power. And so that this part. Now, if you reclose this, then the power will be fed through this path. And this whole gray area will be picked up through this path because it was out from this path, right? So as you see, this is a practical problem. We don't have a many switches, but only this part can be picked. But if the fault happens here, then you cannot pick this area because we only have 2 switch, one here and one here. And if the fault is in between, then we cannot isolate the fault, and then that need to be repaired before we can be closing. If there was another switch here, then we could have isolate from here and pick this region right here, right? So distribution automation and ability to pick the load depends on number of switches, where it's connected, number of feeds, and the rating that can it pick up. Like if this feeder, which is coming from here, if it is not rated to pick this region, then we cannot close it. So everything need to be planned and closed in that way. We can also use this reconfiguration for load balancing if one is high and one is lower voltage or lower frequency. And like this is example that there was more load here, and then what we did is that we closed this one. So this is open, this is closed, and then basically by doing that we were able to balance that. So let me stop here, and then we'll continue talking tomorrow, and if there's any question we can answer. So integrated Vault War will talk tomorrow. So one question is that distribution automation often involves multi-vendor smart devices. That's correct. Using its own protocol, given this diversity, what are the possible way to coordinate or enable interoperability? Yes, it's important question. I think interoperability is possible in multiple ways. So SIM, which is a common information model, is one way. And another one is standardized protocol, like you already said here. So if we have all the devices follow, like let's say 61850, or a certain protocol, which is like for DER there is a 2030.8. So if they follow those kind of protocol, which is designed by IEEE IEC, then we can make the seamless data flow between the different devices in distribution automation. Typically, we try to avoid that. So if you look at the practical utility, they go for, because this is only one feeder with limited number of switches, so they go for only one vendor in that feeder, and then they will put another one. Even with all these standardized practices, it may not become easier. It become easier if you have a same vendor, because sometime even with the standard following, you never know that the semantics of different data, that how they are calling it, and that's why most of the utility try to follow, which is not a best thing to do, but they try to follow similar vendor. Next question, IT or OT, which is more prone to cyber attack? So IT should be more, because IT is public facing, which means that IT is something that enables your email, that enables your billing, as a customer, which means that it should allow everyone to log in and see and exchange information. So it's more public facing, and that's why it can be also easily accessed by attacker. OT, which is more protected, not open to public, it is only meant, it is same infrastructure like IT, but it is configured in a different way. So it is configured in such a way that it will be protecting the system and only helping to operate the grid by exchanging information from substation to devices, from devices to the control center, and all those things. So it should not be open to public, and it means that it's difficult to get into by attacker also. So cyber attack will happen more, but IT attack is not that critical. But OT attack is very critical because it will stop the operation. So it's like a low frequency is OT, but high impact. So low frequency, high impact. IT is high frequency, but low impact. How to handle the overloading condition at the time of reconfiguration? So there are, first thing is that how do we know that it is a overloading, right? So we have to rely on the SCADA and measurement that it is telling us that it is a overloading. Overloading typically, if it is not like 500% or 300%, it is okay for a few minutes, because it will start heating, but we have few minutes to determine that overloading has happened, and I should change and reconfigure in other way so that overloading will be avoided. So I already presented example that how the switch configuration was changed by by sensing that there is overloading on one of the branch, and that's one way of do that. So reconfiguration again and changing the which load is connected where is the only way to avoid the overloading. Other way to avoid the overloading is to disconnect the load, which is not preferred, because you will lose the money to charge that, and distribution utility will not like to do that. But you can use the smart meter to disconnect some of the load which is causing the overload. That's also possible. This is a very good question. Is it possible to localize the cyber attack like fault localization? Right now, fault, when it happens, it does not try to hide itself, right? So the fault is there, it's there. Either it's a tree or something, right? While cyber attackers, if they are there, they are trying to hide themselves. And that's why it's not a similar problem. But it is very interesting idea to apply the similar logic and see that can we locate that where is the cyber attacker. In terms of the difference, which one is trying to hide and one is not, it makes it challenging, but it is possible. The similar technology can be applied just like